Good evening everyone, good evening. I welcome you all again back to JEE Enthuse. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Yes, just let me know in the chat box if I'm audible and visible to everyone. Give me some green signal from the chat box. Hello Harshit, hi Chiranjeeva, hi Chinmay. Hello Manvita, hi Khushi, hello Joker, hi Ria, hi Kaushika, hello Ashwarya. Welcome back everyone, welcome back. Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Yes, hello Khushi, walaikum salam. Perfect guys, perfect. So as you all must be knowing, tonight it's going to be our sixth session from the chapter States of Matter. And what all things we are going to cover in the tonight's session is we are going to talk about something called as effusion and diffusion, right? This is again one of the most important topics from the chapter States of Matter, right? Okay. Perfect. So before starting the session, the ones who are new to the channel, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher writer on this JEE Enthuse channel, right? The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this JEE Enthuse channel. Yeah? You can let me know in the chat box if you guys are super duper excited about the session, right? Let me know in the chat box if you guys are super duper excited about the session. Yes, Kaushika, exactly. Just let me know in the chat box if you guys are super duper excited about the session. Well, Krish, you just refresh your page once because on my side the connectivity is all okay. Yes. Perfect, guys. Perfect. Wonderful. So, without wasting a lot of your time, let's get started. Let's get going with something called as effusion and diffusion, right? First, I'll be giving you the definition of this effusion and diffusion. Then we'll be talking about something important called as Graham's law of effusion. Okay. So, and after that, we'll be doing some problems by means of which all the concepts will get clear to you. Okay. So let's get going. Let's get started with something called as effusion. Okay. What is effusion all about? So let me define the term effusion first, then I'll make you understand what this effusion exactly is all about, right? I want you guys to note down every single thing which I'll be writing over here on the screen. Yes? People, effusion, it is defined as the escaping out of gas molecules, through a small hole or aperture when the gas is under pressure, Okay. What is meant by all this? What is meant by this definition? See guys, effusion as per the definition is concerned, it is defined as the escaping out of gas molecules through the hole or aperture when the gas is under pressure. Okay, what it means exactly, understand. For example, I have got a container over here. Let's say I've got a container over here which is right now closed on all the sides. Yes, I have got the container which is closed on all the sides. Now in this container, for example, I have kept an ideal gas over here in this container. Okay, let's assume I have kept an ideal gas in this container, right? Now people, as per the property of gas is concerned, we know the molecules of the gas, they'll be always in continuous random motion, due to which they'll be colliding with each other, and at the same time they'll be colliding with the walls of container as well, due to which there will be some pressure of this gas, right? So basically this gas would be exerting some pressure on the walls of the container, right? Let's assume the pressure of the gas right now I'm denoting by P, okay? P is the pressure of the gas right now, right? Now if I'll make a small hole over here somewhere, right? In the container, I have made a small hole over here. What's going to happen? Can I say through this hole, some of the gas molecules will start leaving the container, right? Can I say some of the gas molecules will start escaping out? Yes. And people, at the same time, the escaping out of gas molecules through the hole when the gas is under pressure, this is something which I call as effusion. As simple as that, right? So what is effusion all about? It is basically the escaping out of the gas molecules through the hole when the gas is under pressure, okay? And the gas which is coming out of the container, let me call this gas as the effused gas. Let me call this gas over here as the effused gas, right? As simple as that. So escaping out of gas molecules through the hole when the gas is under pressure, that's something which I'm calling as effusion. Point number one. Point number one, right? Now people, outside this container, I'll say there will be atmosphere over here, right? Outside this container, there will be atmosphere on all the sides, okay? This is atmosphere which contains gases, okay? Now people, what is going to happen? The gas which is coming out of the container, the effused gas I'm talking about, right? The effused gas, it is going to spontaneously, the effused gas will be spontaneously intermixing with the atmosphere to form a homogeneous mixture. Okay, first what happens? The gas comes out of the container through the small hole, right? After that, the effused gas spontaneously it intermixes with the atmosphere to form the homogeneous mixture, and that spontaneous intermixing of the effused gas with the atmosphere to form the homogeneous mixture, that's something which I call as diffusion. That's something which I call as diffusion, right? So if I ask you, what is diffusion all about? You can define the term diffusion from now onwards now. Yes. So what is diffusion all about? Diffusion is simply defined as the spontaneous intermixing of the escaped gas with the atmosphere to form a homogeneous mixture. Right? So I'm sure the two terminologies are clear to you. Number one, that was effusion. Number two, that is diffusion, right? So what is effusion all about? Effusion is simply the escaping out of the gas molecules through the hole when the gas is under pressure. That's something which I call as effusion. And the spontaneous intermixing of the effused gas with the atmosphere to form the homogeneous mixture, that's something which I call as diffusion, okay? Can I say simply a statement? Can I say effusion is always followed by diffusion, right? I can say this thing as well. Effusion is always followed by diffusion, correct? First, effusion happens, and after that, suddenly diffusion happens. As simple as that, okay? So people, I'm sure these three things are clear to you. Number one, effusion. That is the escaping out of the gas molecules through the hole or aperture when the gas is under pressure. That's something which I call as effusion. Number two, the escaped gas spontaneously intermixes with the atmosphere and forms the homogeneous mixture. And that spontaneous intermixing of escaped gas with the atmosphere to form the homogeneous mixture, that's something which I call as diffusion. And you got to know effusion is always followed by diffusion, right? Now let's talk about something else, which is what we call as a rate of effusion or diffusion. How do we define the term rate of effusion over here? This is important, okay, and simple at the same time. If I talk about something called as rate of effusion, how do we define it? I define rate of effusion in two ways. Number one, rate of effusion is defined as the volume of the gas or number of moles of the gas escaped per unit time. This is the simplest way by means of which I can define something called as rate of effusion. Rate of effusion is simply defined as the volume of the gas escaped or the number of moles of the gas escaped through the small hole per unit time, right? Which can be understood like this. let's assume this is the container which I have, and I have put one hole in the container, and there is basically an ideal gas in the container, for example, okay? Now I can say some of the gas will be coming out of the container right here. Let's assume V ml of gas is coming out of the container in time t seconds. Let's assume some V ml of gas is coming out of the container in time t seconds. Or let's assume it like this. Let's assume n moles of the gas. Let's assume n moles of the gas is coming out of the container in time t seconds. How can I define rate of effusion of the gas? It is simply defined, I'll say rate of effusion is simply defined as volume of the gas escaped, that's V ml, divided by time taken, which is t seconds. Or I can say number of moles of the gas escaped divided by time taken. These are the two ways by means of which simply you can define something called as rate of effusion. Okay, so rate of effusion is nothing, it is simple. Rate of effusion is basically the volume of the gas which will be coming out of the container in time t, or I can say number of moles of the gas coming out of the container in the given time t. Okay, right? I'm sure this again clear to you. It's a very, very simple thing, right? Okay. Now the actual stuff which we have to talk about right here, that's something called as Graham's law of effusion. That's something called as Graham's law of effusion. Now what is that Graham's law of effusion and diffusion all about? Okay, let's understand that. Let's derive some formulas and then let's try to apply those formulas in the equations, right? Okay, so people, rate of effusion is basically defined as the volume of the gas or the number of moles of the gas escaped per unit time. It's not per unit mole, sorry. Okay, just a second. Now let's talk about something called as Graham's law of effusion. Okay, just a second. All right, so what is this Graham's law of effusion all about? Understand properly what I'm going to say. Okay, understand properly. Let's talk about something called as Graham's law of effusion. Okay, as per the Graham's law of effusion is concerned, we say rate of effusion of a gas is inversely proportional to the square root of molar mass of the gas. This is the simplest statement of the Graham's law of effusion. Okay, rate of effusion of the gas is inversely proportional to square root of molar mass of the gas. Or I can say more the molar mass of the gas, less is going to be the rate with which the gas comes out of the container, right? Or you can say more the molar mass of the gas, less will be the rate of effusion of the gas. Similarly, less the molar mass of the gas, more is going to be the rate of effusion. More is going to be the speed with which the gas comes out of the container. As simple as that. Okay, right? So I can say rate of effusion. If I remove this proportionality sign, I'll put a constant over here, which I'm denoting by K, divided by square root of molar mass of the gas, right? Now the point is, where do I use this equation? Or before using the equation, let me tell you one important thing. More the molar mass of the gas, less is going to be the rate of effusion, less is going to be the speed with which the gas comes out of the container, right? And if I say less the molar mass of the gas, that means more will be the rate of effusion. That means more will be the speed with which the gas comes out of the container, right? Okay. Now, where do I use this formula? Where do I use this equation? Understand properly what I'm going to say. Yeah, I'm sure till here it's clear to you. Yeah. Now, let me show you where do I exactly use this. I got to know rate of effusion is equal to constant K divided by square root of molar mass of the gas as per your Graham's law of effusion is concerned, right? Yes. Now look here. Let's assume this is the container which I've taken. The container contains gas A. There is gas A present in the container. Similarly, for example, I have got some gas B in the container. I have got some gas B in the container, right? I have got gas A and gas B present in two containers right now. Okay. Let's assume the pressure and temperature of both the gases are same. That means I'm keeping the gases under similar conditions. The gases are kept under similar conditions. Okay, I'm keeping the pressure and the temperature of the gas same. For both the gases, their pressure is same, their temperature is same. That means the gases are present at similar conditions, right? Now people understand. I have created a hole in this container, and at the same time I have created the hole in this container as well. Yes. So there will be some gas coming out of the container. Let's assume VA/ml of gas A is coming out of the container in time TA seconds, or let's assume NA moles of gas A are coming out of the container in time TA seconds, right? Similarly, let's assume VB/ml of gas B is coming out of the container in time TB seconds, or I can say NB are the moles of the gas B which are coming out of the container in time TB seconds, right? Let's assume the molar mass of gas A is ME, the molar mass of gas B is MB. Okay, this is something which I'm doing, right? Understand properly, guys. See, I've taken two ideal gases, gas A and gas B. Their molar masses are MA and MB respectively, okay? Both the gases are present at same pressure and temperature. That means both the gases are present at the similar conditions, yes? Now, let's assume VA/ml of gas A is coming out of the container in time TA seconds, or I can say NA moles of gas A are coming out of the container in time TA seconds, yes? And at the same time, let's assume VB/ml of gas B are coming out of the container in time TB seconds, or I can say NB moles of gas B are coming out of the container in time TB seconds, right? Now what I'll be doing, if I'll be using this Gram's law of effusion formula for the gas A, can I say something like this? Can I say rate of effusion of gas A is equal to constant divided by square root of molar mass of gas A, right? Similarly, if I use the rate of effusion equation for the gas B, I'll say rate of effusion of gas B is equal to K divided by square root of molar mass of gas B, right? Let's keep this as equation number 1. Let's keep this as equation number 2, right? Okay. People, if I'll simply divide these two equations, what do I get? If I divide these two equations, I'll be getting rate of effusion of gas A divided by rate of effusion of gas B is equal to square root of molar mass of gas B divided by molar mass of gas A, right? This is the simplest formula which I got right now. Yes? Okay. Now people understand. What is this RA over here? RA is something which I call as the rate of effusion of gas A, which I can say volume of gas A coming out of the container in time TA seconds, whole divided by, what is RB? RB is basically volume of gas B coming out of the container in time TB seconds, right? Or I can write the same thing in terms of moles as well. I can say rate of effusion of gas A will be equal to number of moles of gas A coming out of the container in time TA seconds, whole divided by number of moles of gas B coming out of the container in time TB seconds. Yes? Right? Now one more result. This is one important equation which I'll be using in the questions in which I need to compare the rates of effusions of two gases. Whenever I'll be given with two gases which are present at similar conditions, if I need to compare the rates of effusions, if I need to compare the speeds with which the gases comes out of the container, right? I'll be using this equation. Yes. And at the same time, if you'll see one more thing, people, we have studied density form of ideal gas equation, if you remember. As per your density form of ideal gas equation is concerned, we say Pm is equal to dRT, right? Since over here, pressure and temperature I'm keeping constant, same, R is already constant, so can I say molar mass is directly proportional to density? Absolutely. So wherever in this equation you're seeing the term molar mass, you're going to replace the term molar mass by the corresponding density of the gas, right? Yes? Okay, as simple as that. Okay, right? So people, Pm is equal to dRT. This is something which I call as density form of ideal gas equation. Since I'm keeping the pressure and temperature constant, so I can say molar mass is directly proportional to density of the gas. So people understand. So wherever in this equation you are seeing the term molar mass, you are going to replace the term molar mass by their corresponding density of the gas. Okay, that means you can equate it to one more thing over here. It is going to be equal to under root of, instead of molar mass of B, I can say density of B. Instead of molar mass of A, I can say density of A, right? Okay, this is one equation which I'll be using only when I need to compare the rates of effusions of two gases present at same pressure and temperature, right? Let me know in the chat box if everything is clear till here. Jayashri, just wait for it. I'll let you know what will happen on changing the pressure. Rehan, my JEE batch on the long term, on the actual Vedantu platform, it didn't start yet. Okay, I'll let you know when it'll start, right? I'll let you know, guys, about my long-term batch, about my JEE long-term batch. It didn't start yet. It's most probably going to start this month, the upcoming month. I'll let you know about it, right? Perfect. Wonderful. Thank you, Sharon. All right, moving on. Let's move on to something else, yeah? This is one equation which I got over here. But this equation is only valid. This equation I'll be only using when I need to compare the rates of effusions of two gases which are present at same pressure and temperature, okay? Yes. Now, people, few more things. I'm sure you would have noted down these results. Now, let's talk about something else, okay? What is that going to be? See. If, for example, pressure of the two gases is not same, if the pressure of two gases is not same, if the pressure keeps on changing, but temperature of the gases is same, okay? If I keep the temperature of the gases same, but the pressure of the gases I'm changing, what do I do at that time? Understand properly. Let's assume this is gas A in the container, right? Its molar mass is Ma, okay? Let's assume the pressure of this gas A right here is Pa, okay? Similarly, I've got one more gas B in this container. This is gas B in this container. Let's assume molar mass of this gas is Mb. Let's assume the pressure of this gas is simply Pb. And I'm keeping the temperature of both these gases same. I'm keeping temperature of both these gases same, okay? Now we will understand. Let's assume VAml of gas A is coming out of the container in time T seconds. Let's assume VBml of gas B is coming out of the container in time TB seconds. Or let's assume it like this. NA be the moles of the gas A coming out of the container in time TA seconds. NB, let's assume, are the moles of gas B which are coming out of the container in time TB seconds, right? People, it's a normal, use your common sense. If, for example, pressure of gas A is greater than pressure of gas B, leave the molar mass aside, leave the temperature aside. If by chance pressure of gas A in the container is more, what is going to happen? If pressure of this gas A will be more, I think the speed with which the gas A comes out of the container will be more, right? If the pressure of gas A is more in this container, so I should say the speed with which gas A comes out of the container, that should be more. That means the rate of effusion will be more in the first case, okay? So can I say something like this? Can I say rate of effusion is directly proportional to pressure of the gas, right? More the pressure of the gas, more the rate with which the gas comes out of the container, more the speed with which the gas comes out of the container, yeah? Yes. So rate of effusion is directly proportional to pressure of the gas. And we already know it's inversely proportional to square root of molar mass of the gas. We already know it's inversely proportional to square root of molar mass of the gas, right? So people, I'll be getting one equation right here. Rate of effusion is equal to K, which is a constant, P divided by square root of molar mass of the gas, yes? Now where do I use this equation? Understand properly. First thing, I'm going to apply this equation for gas A over here, right? I'm going to apply this equation for gas A over here. So I can say rate of effusion of gas A is equal to K multiplied by pressure of gas A divided by square root of molar mass of gas A. Yes? Right? Similarly, I can say rate of effusion of gas B is equal to K multiplied by pressure of gas B divided by square root of molar mass of gas B, correct? Let's keep this as equation number 1. Let's keep this as equation number 2. If I simply divide these two equations, what do I get? I can clearly say rate of effusion of gas A divided by rate of effusion of gas B is equal to pressure of gas A divided by pressure of gas B square root of molar mass of gas B divided by molar mass of gas A, right? This is one important equation which I got over here. But remember, this equation I'll be only using when the pressure of the gases will be different, but the temperature of the gases will be same. Okay, this is the equation I'll be using then only, right? Yes. Now we will understand one more thing. What is RA? RA is something which I call as rate of effusion of gas A, which can be written as volume of gas A coming out of the container in time TA seconds divided by rate of effusion of gas B, which is going to be volume of gas B coming out of the container in time TB seconds, which can be also written as Rate of effusion of gas A I can write as number of moles of gas A, which is coming out of the container, divided by time t seconds, whole divided by number of moles of gas B coming out of the container in time t b seconds, right? This is basically the equation. This is basically the equation which I'll be only using when I'll be having two gases and I need to compare their rates, but at the same time the gases are present at the different pressures, but their temperatures are same, right? Can you let me know, is this relation clear to you, so that I can show you the equations by means of which all your concepts will get cleared, right? Let me know in the chat box if everything is clear till here. Let me know. Sharon, in order to compare the rates of effusions, you definitely need to divide these two, right? Okay, in order to compare the rates of effusions of the gases. No, Jayashri, you cannot write it in the density form because that is only valid when the pressure and temperature are same. Okay. Raghuthaman, I'll be doing that soon. Just wait for it. Okay. Perfect, guys. Perfect. So let me show you some questions. By solving those questions, I believe your concepts will get clear, right? The first and the basic question which I'll be solving as per this effusion over here. But before that, these are the equations which I gave you right now. Yes, these are the equations which I gave you. Now let's try to use these equations in the form of questions. This is the first question on your screen. You can give it a try. You can let me know the answer of this question in the chat box. Give it a try first. Give it a try. It's a very simple question, okay? Sharon, gram equivalent concept is different, okay? Gram equivalent concept is different. That is something which I'll be teaching you in redox reactions, not here. Thank you, Priyanshu. Okay, give it a try. You can let me know its answer in the chat box. I'm looking at your chats only. Yes. Give it a try. Perfect, guys. So let's see how this question is to be solved. Understand, it's a very, very simple and basic and ordinary question which I've given to you right here, so that you know how to use the basic formulas. Yes? Understand properly. Well, people, the first thing that is striking my mind over here, something is mentioned as similar conditions. Similar conditions means I'm keeping the pressure and temperature same. I'm keeping the pressure and temperature of the gases as same, right? So which formulas I'm going to use? Am I going to use the first formula or second formula? I'll be definitely using the first formula to solve the equation, right? So as per the equation, we have got SO2 gas right here in the container. This is the SO2 gas right here in the container. And I've got one more container which contains O2 gas over here, right? Which contains O2 gas, I guess. Yes. Just a second. Which contains what? Yes, O2 gas. So I've got two containers. So one containing SO2 gas, one containing O2 gas, right? It's mentioned in the equation that a sample of SO2 gas escapes through a hole in 122 seconds. A sample of SO2 gas escapes through a hole in 122 seconds. Let's assume V ml of SO2 gas is escaping out of the container in 122 seconds, right? Because it's mentioned as per the equation, a sample of SO2 gas escapes through the hole in 122 seconds. I'm assuming some V ml of SO2 gas coming out of the container in 122 seconds. Yes. Okay. Now what do we need to check? How long will it take for oxygen to effuse the same volume, right? So what do I need to check? I need to check how much time oxygen takes to effuse the same VML, right? I need to calculate the time taken by the oxygen gas to effuse the same VML. So I'm assuming right here, the volume of O2 that's coming out of the container is again VML, right? And I need to calculate the time taken by O2 gas to effuse the same VML over here, right? Okay. So this is the equation. Let me make you understand once more. So this is the SO2 gas. Let's assume VML of SO2 is coming out of the container in 122 seconds. I need to check if VML of O2 gas comes out of the container, how much time it takes to come out, okay? The conditions are similar. That means the two gases are present under similar conditions. Their pressure and temperature both are same. So I'll be simply comparing their rates. I can say rate of effusion of SO2 divided by rate of effusion of O2 will be equal to square root of molar mass of O2 divided by molar mass of SO2. I can say something like this, right? Well, we will rate of effusion of SO2, I can say volume of SO2 coming out of the container, which is VmL, divided by time taken by SO2 to come out of the container, that's 122 seconds. Rate of effusion of O2 will be equal to volume of O2 coming out of the container, that's VmL, divided by time taken by O2, which is something which I have to calculate. Square root of molar mass of O2 is simply 32 grams. Molar mass of SO2 is 64 grams. We say we cancel. What do I get over here? I get something as time taken by O2 whole divided by 122 is equal to 1 divided by under root 2. 1 divided by root 2. So you get something time taken by O2 to effuse the VmL. It's going to be simply 122 divided by root 2 seconds. Or you can write it like this as well. I can say time taken by O2 gas to effuse the VmL over here. That's going to be 61 under root 2 seconds, right? This is the final answer. So this much time O2 gas takes to effuse the same VmL volume which was effused by SO2 gas, right? Let me know in the chat box if it is clear to everyone. Let me know in the chat box if it is clear to everyone. Yes, Jayashree, it will be approximately 86.2. 86.2 seconds approximately it's going to be, yeah? Just give me some green signal from the chat box so that I'll get to know whether it's clear to you or not. Okay? Let me know fast. Let me know fast. Give me some green signal from the chat box so that I can move on. So that I can move on. It's okay, Dinesh. Take care. All right, so let's move on to one more question. Let me see if you can solve that question or not. This is the question on your screen. Give it a try, give it a try. Let me know its answer. Give it a try. A very, very simple and basic question again. You all can solve this one, I believe. 50 ml of each gas A and B takes 150 seconds and 200 seconds respectively to effuse through a pinhole under similar conditions. If the molar mass of gas B is 36 grams per mole, what would be the molar mass of A? Yes, Nadeem, I'll be doing that. No issues. Right? 50 ml of each gas A and B takes 150 seconds and 200 seconds respectively to effuse through a pinhole under similar conditions. If the molar mass of gas B is 36 grams per mole, what would be the molar mass of gas A? This is the question which is given to me. Give it a try and let me know its answer fast. Give it a try, guys. Give it a try fast. Give it a try fast. What do you think should be the answer of this question? What do you think? Well, people are saying it's option A, is that? That's good. That's cool. Yes. Perfecto. So let's see. Exactly, guys, all of you are right. It's going to be option A. So basically, without using any sort of formula, we can solve this question. And how can we do that? Have a look. So it's mentioned in the question that 50 ml of each gas A and B. So I have got gas A, this is gas B. 50 ml of gas A is escaping out of the container, and at the same time 50 ml of gas B is escaping out from the container as well, right? So 50 ml of gas A and 50 ml of gas B are escaping out of the container. Well, it's mentioned in the question the time taken by gas A to effuse 50 ml of it. The time taken by gas A to effuse 50 ml of it, that's given to me as 150 seconds. And time taken by gas B to effuse 50 ml of it, that's given to me as 200 seconds, right? Okay. People understand. This gas is taking lesser time to escape out. This gas is taking more time to escape out, right? This gas is taking lesser time to escape out. So what does that mean? That means the speed with which gas A comes out of the container, that's more. The speed with which gas A comes out of the container, that's more. So what does that mean? That means rate of effusion of gas A is greater than rate of effusion of gas B. Yes. We already know something. Rate of effusion is inversely proportional to square root of molar mass. Can I say more the molar mass of the gas, less will be the rate of effusion? Okay. More the molar mass of the gas, less will be the rate of effusion. Or more the rate of effusion, less is the molar mass of the gas, right? So I got to know rate of effusion of A is greater than rate of effusion of B. Okay. So what I can say, more the rate of effusion, less the molar mass. I can say molar mass of A should be less than molar mass of B. Okay. What is the molar mass of B that's given to me? Molar mass of B is given to me as 36 grams per mole. That means molar mass of A should be less than 36. Molar mass of A should be less than 36. And there is only one option that's less than 36. That's 20.25, right? Yes. Let me know in the chat box if it is clear. Well, atomic structure, I'll be resuming on Tuesday on NEET Elite channel. Yeah? Let me know in the chat box if it is clear to you guys fast. Perfect. Let me know fast, let me know fast, let me know fast. Yes? Perfecto. You can solve the same question by means of formula as well, right? You can say rate of effusion of gas A divided by rate of effusion of gas B is equal to square root of molar mass of B divided by molar mass of A. That's it. Yes? Okay. Let's move on and let's try to solve one more question over here. Okay, understand this question and let's see how this question is to be solved, right? It's a very, very simple question again, and I'm sure you can solve it easily. Yeah? What the question is all about. What the question is all about. Understand. See guys, 1 mole of N2 gas at 0.8 atm takes 38 seconds to diffuse through a pinhole, right? While 1 mole of an unknown xenon fluoride at 1.6 atm takes 57 seconds to diffuse through the same hole. The formula of the unknown xenon fluoride will be. Okay? Well, in order to keep it simple, I'll remove this diffuse term. I'll keep effuse over here. Okay? I'll keep effuse over here so that you won't get confused at all. Okay? Now see guys how to solve this sort of equation. It's a very simple question. So basically, this is a container which is given to me, and this container contains N2 gas. What is the pressure of N2 gas in this container? It's given to me as 0.8 atm, right? And we have got one more container. This is one more container. This container contains unknown xenon fluoride. It can be XCF2, it can be XCF4, it can be XCF6. You have no idea what it is exactly. So I'm assuming the formula of this unknown xenon fluoride as XEFX. Okay? Right? Basically, I need to get the molecular formula of this unknown xenon fluoride. I need to see exactly, is it going to be XCF2? Is it going to be XCF4? Is it going to be XCF6? Or what it's going to be, right? Basically, I need to get the value of this X over here. Yes? Okay. Now, we will see how this question is to be solved. Understand. Well, the first thing, the pressure of XEFX, it's given to me as 1.6 atm. The pressure of this XCFX gas, it's given to me as 1.6 atm, right? It's mentioned in the equation that 1 mole of N2 gas is escaping out. Number of moles of N2 gas that are coming out of the container is 1. And 1 mole of N2 gas is coming out of the container in 38 seconds. So time taken by this N2 gas is simply 38 seconds. Similarly, it's mentioned over here that 1 mole of XEF2 is also effusing out, right? It's mentioned that 1 mole of this unknown xenon fluoride is escaping out in how much time? It's taking some 57 seconds to escape out, right? It's taking some 57 seconds to effuse. Okay, I need to get the molecular formula of this XCFX. Okay, so let me make you understand the equation again. 1 mole of N2 gas is escaping out in 38 seconds, and 1 mole of unknown xenon fluoride is escaping out in 57 seconds, right? I need to check the molecular formula of XEFX. So what should I be doing? Simple. Is the pressure of the gases same or different? The pressure of the gases is different, right? So I'll be using the relation as rate of effusion of N2 divided by rate of effusion of XEFX will be equal pressure of N2 divided by pressure of XCFX square root of molar mass of XCFX, okay, divided by molar mass of N2 gas. Okay, this is something which I got till now. Now, instead of rate of effusion of N2, I can say number of moles of N2 which are coming out of the container divided by time taken by N2 whole divided by rate of effusion of XCFX. That's going to be number of moles of XCFX coming out of the container divided by time taken by XCFX. Okay. So first of all, how many moles of N2 are escaping out? 1. How many moles of XCFX are escaping out? 1. So this term and this term will get cancelled out. So I'll be getting time taken by unknown xenon fluoride to escape 1 mole of it divided by time taken by N2 gas will be equal pressure of N2 gas, which is given to me as 0.8 divided by pressure of XCFX, that's 1.6, square root of molar mass of XCFX I need to calculate divided by molar mass of N2 is 28. Okay. Now time taken by XCFX is how much? It's 57. It's 57. This is 38. So I'm going to write 57 divided by 38 over here. It is 57 divided by 38. So this is going to be 1 by 2. Okay, this is 19.3. This is 19.2. Okay, this 2 and 2 got cancelled. So I got something as 3 is equal to square root of molar mass of XCFX divided by 28. Okay, if I square on both the sides, this should be 9 is equal to molar mass of XCFX divided by 28. So from here, you'll be getting the molar mass of unknown xenon fluoride, and the molar mass of unknown xenon fluoride will come out to be 252 grams per mole. So you got the molar mass of unknown xenon fluoride. You got the molar mass of unknown xenon fluoride. So what does it mean? It simply means the molecular mass of XCFX, the molecular mass of XCFX is going to be 252U. Okay, this is the molecular mass. Absolutely, this is the molecular mass. What is molecular mass basically all about? Molecular mass of XCFX will be the sum of atomic masses of these atoms, the sum of atomic mass of these elements. Let the atomic mass of Xe, you all must be knowing, that's 131. 131, U is the atomic mass of Xe xenon, plus X times the atomic mass of fluorine, that's 19, is equal to 252 over here. While when you solve it, you get the value of X approximately equal to 6. And this X basically I was supposed to calculate, the small x I was supposed to calculate. So you got the formula of the unknown xenon fluoride as XCF6, right? This is something which I was supposed to calculate. You can let me know in the chat box if it's clear to you fast. You can let me know in the chat box if it's clear to you. Yes, exactly, it's going to be XCF6. Right, Shreya? Right, Jayashree? Exactly. So first thing what I did over here was, I calculated the molar mass of unknown xenon fluoride, and after calculating the molar mass of unknown xenon fluoride, I calculated basically the molecular mass of unknown xenon fluoride, and molecular mass of unknown xenon fluoride, it's simply going to be atomic mass of xenon plus X times the atomic mass of fluorine. That's basically equal to 252. So from here, you get the value of X almost equal to 6, yeah? As simple as that, okay? Perfecto. Yes. So let's move on to one more question. Let me see if you can solve that question or not. Okay, one more question on the screen. You can kill this question. Let me know its answer in the chat box. It's a very, very simple question again. So X ml of H2 gas effuses through a hole in 5 seconds at 5 atm. The time taken by O2 gas to effuse the same volume at 10 atm will be. This is the question on your screen. You need to give it a try. Yes, Bhagya, exactly. Give it a try. Give it a try. Give it a try. Let me know its answer fast. Well, it's a very, very simple question. You can check it out to understand how it's to be solved, right? See guys, how it's to be solved. Understand properly. Hello, Jaya, Seeli. Welcome to the channel. Welcome, welcome. Okay. See guys, how this question is to be solved. Well, X ml of H2 gas effuses through a hole in 5 seconds. So basically, I have got H2 gas in the container. Yes, I have got some H2 gas in the container. And it's mentioned that X ml of H2 gas is escaping out. So volume of H2 gas that's coming out of the container is xml, right? And time taken by H2 gas to escape 5 ml of it is 5 seconds, right? This is given to me as 5 seconds. Okay, what is the pressure of H2 gas that's given to me? Pressure of H2 gas right here is given to me as 5 atm. It's given to me as 5 atm, right? Now I've got one more container as well. This is the container which I have. In this container, I've got O2 gas. Yes. And what do I need to calculate? The time taken by O2 gas to effuse the same volume. So I'm assuming volume of O2 gas which is coming out of the container is equal to X only. So let's assume X ml of O2 gas is coming out of this container as well, right? I need to get the time taken by O2 gas to effuse X ml of it. I need to get to know the time taken by O2 gas to effuse the X ml of it. And at the same time, one thing we are given with, that's the pressure of O2 gas. Pressure of O2 gas is given to me as 10 atm. Well, we can solve it, we can get the answer. It's a very simple one, just the formula based question, right? So can I say something like this? Can I say rate of effusion of H2 divided by rate of effusion of O2 will be equal to pressure of H2 divided by pressure of O2 square root of molar mass of O2 divided by molar mass of H2. Yes, I can write it like this. Okay. Now people, rate of effusion of H2. I can say rate of effusion of H2 will be equal to volume of H2 which is coming out of the container divided by time taken by H2, that's 5 seconds, whole divided by rate of effusion of O2 will be equal to volume of O2 that's coming out of the container, that's X ml, divided by time taken, which I need to calculate, right? Let's try to equate these two things over here. Let's try to equate these two things. So what I'll be getting over here, understand, I'll be writing something like this. First thing, this X and X will get cancelled out. So what I'll be getting right here, I'll be getting TO2 divided by 5. TO2 divided by 5 is equal to TO2 divided by 5 is equal to pressure of H2 gas, it's given to me as 5 atm. Pressure of O2 gas is given to me as 10 atm. Square root of molar mass of O2, all of you must be knowing, that's 32. Molar mass of H2, all of you must be knowing, that's 2, right? Yes, so it's 5.1, it's 5.2, right? So you get something as TO2 divided by 5 is equal to 1 divided by 2 multiplied by, it's going to be under root of 16, under root of 16 is 4, and 4 divided by 2 is 2, right? So from over here, you'll be getting something as 2. So if you solve it, you'll be getting the time taken by O2 gas to effuse X ml of it is simply 10 seconds, right? So you got to know the time taken by O2 gas to effuse the same X ml over here, which came out to be 10 seconds, right? Okay. This was the question. Now people, there is one question which I'll be giving you as the homework. There is one question which I'll be giving you as the homework. And the question is something like this. Understand properly what I'm going to say. I'm given with a cylinder. This is a cylinder which is given to me. This is a cylinder which is given to me. Okay, before going to this question, let me tell you one thing. Remember, when NH3 gas reacts with HCl gas, it leads to the formation of NH4Cl solid. It leads to the formation of NH4Cl solid, right? Remember this, okay? When NH3 gas reacts with HCl gas, it leads to the formation of something solid, right? Well, as per this question, I'm given with a cylinder. The area of cross section of this cylinder is A. The length of this cylinder is, for example, 1 meter, or let's keep it as 1 meter only, so that your calculation becomes simple, right? I'm given with a cylinder. Its length is given to me as 1 meter. Yes. Now, for example, on this side, from this side, I'm introducing NH3 gas, and at the same time, from the another end, I'm introducing HCl gas. Okay, so on both its sides, I'm introducing two gases at the same time. On this side, I'm introducing NH3. On this side, I'm introducing HCl. So can I say when these two gases will start coming closer, because I'm introducing the two gases on the opposite sides, so these two gases will be coming closer, and there will be a time when these two gases will touch, when these two gases will meet, right? And once these gases meet, they'll start react. They will lead to the formation of NH4Cl, right? They lead to the formation of NH4Cl. Yes. They lead to the formation of NH4Cl. And that NH4Cl is a solid. So that solid gets settled down at the bottom of the container. that solid gets settled down at the bottom of the container. I'm assuming that solid is getting settled down over here. You need to calculate one thing. You need to calculate the distance. This is first of all the precipitate which is getting deposited over here. This is your NH4Cl which is getting deposited over here, right? Now you need to calculate the distance from the NH3 end to this precipitate point, which I'm representing by X. You need to let me know the value of X over here. This is the question. This is the question, right? I'm sure you understood this question, right? Do let me know this X over here. Do let me know this distance X over here. This is going to be your homework. You are going to let me know the value of X in the comment box afterwards. Yes? Right? Omar, I'll see. I don't remember exactly what was the homework question which I gave you in the Atomic Structure Lecture 1. I'll take it out. Bhagya, for NEET aspirants, I take classes on NEET Elite channel. Okay. Farhan, I'll let you know soon. Once I get to know the batch for the JEE which I'll be taking on the actual Vedantu platform, I'll be letting you know that as well. Yes, Jayashri, I have finished already the NEET, chemical kinetics in NEET Elite channel. That's great, Mufiza. That's wonderful. Even I'm from Kashmir. Yes. Perfect, guys. So with this, I'll take a leave. I'm sure you would have enjoyed the session. Yes. And there is one important thing which I need to tell you right now. What is that going to be? If you have not joined into the actual Vedantu platform yet, if you have not joined into the actual Vedantu classrooms yet, apart from the YouTube sessions, right? There are actual Vedantu classrooms on the platform that's called as Wave platform, right? Okay. So how to become part of the actual classrooms of Vedantu, right? You need to take any of these plans which I have mentioned over here. We have 3 plans for you. You can select any one of these plans, and these are basically your 2-year package. This is a 2-year package for this light program over here. This is a 2-year package for this classic program over here. This is the 2-year program for this plus program over here. Yes, Omar, definitely. And at the same time, no need to pay this much of amount in one go. You can pay this much amount in installments as well in the form of EMI. Okay, Vedantu has kept an option for that as well, right? Okay, and people, if you are new to Vedantu, you have no idea how the actual Vedantu platforms look like. Will I get benefited from the sessions on the actual Vedantu platform? For that, Vedantu has created an option for you guys. Okay, what is that? You can take the plan for a month. Okay, this is the 1 month fee for this plan, 1 month fee for this plan, 1 month fee for this plan. So take the plan for a month. If you think you are getting benefit, then go for the actual 2-year classroom program. And I'm sure you would love it, and you will definitely enroll into the 2-year classroom program, right? So do take any one of these plans, right? For a month, check it out. If it's working for you, then go for it. And how to take the plans? There's a link in the description box of the video. Basically, you need to click on that link. After clicking on that link, you need to use the coupon code as WBPRO. This is the coupon code which you guys will be using, and on using this coupon code, you'll be getting some additional 10-20% off as well, right? So do get enrolled in this one. Yes? Yes, Jayasri, it's similar. Okay? And there is one more link in the description box of the video. That's for the Telegram. Do click on the link, get added to the Telegram group, and stay updated about the classes. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Well, people, it was nice meeting you. I'll see you guys tomorrow. Not tomorrow, day after tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.